I'm Todd Burns, senior level geomatics student at the University of Alaska Anchorage, and I'd like to tell you about my Capstone project. First, however, a bit of relevant background on some of the topics at hand. Synthetic aperture radar, or SAR, is an active remote sensing technology using microwave radar with a synthetically large aperture derived from a receiver in motion to acquire imagery independent of lighting or weather conditions. However, due to its unique characteristics, the images don't look like the RGB image depicted here, but appear as noise like this, and specialized knowledge to interpret and complex processing techniques, both literally and figuratively, are required to utilize the data. Interferometric SAR processing, or INSAR, allows one to derive change values from the phase differences detected between repeat SAR images. INSAR processing requires even more specialized software. Open source software is software whose source code is, well, open. Users can review, modify it, and redistribute it. This means it's not only freely shareable, but also almost always free of charge. This also means it can be challenged to use and integrate various software packages. Open source software solutions are, however, available for almost every computing need, including INSAR processing. With all that in mind, the goal of this project was using modest hardware, free open source software to assemble a SAR workstation capable of generating interferometric SAR results from freely available SAR data. The hardware used was a small form factor Intel i5 business class desktop, nothing special. To help improve processing performance, additional memory was added and the internal hard drive was replaced with an SSD. This was paired with an external hard drive to provide additional storage. Based on its relative ease of installation, consistent user experience, and widespread community support, the Linux operating system chosen was Ubuntu. Additionally, QGIS and open source GIS and Google Earth Pro were both installed to facilitate result reviews and any future analysis that might be needed. The image data used was acquired by the European Space Agency's Sentinel-1A, a C-band SAR satellite whose images are made freely available by the ESA, and these were downloaded from the Alaska Satellite Facility. The SAR-specific software used to process this data included the ESA's own SNAP, or Sentinel Application Platform, Snafu by Curtis Chin, Stamps by Andy Hooper, as well as Triangle by Jonathan Shuchuk. Obtaining these required pieces of software, that was the easy part. But apart from Snap, which was quite user-friendly, getting the required software integrated and functional, as well as learning the idiosyncrasies of the command line terminal-based programs in order to produce the desired results, that was a real challenge. It demanded extensive review of a variety of computing and remote sensing topics. The first processed examples I'll cover that demonstrate the capabilities of the functioning system involve differential interferometry, or DINSAR, a technique wherein the topographic contribution to the recorded interferometric phase shift between repeat SAR images is removed. This allows for the identification of ground movement. DINSAR processing was accomplished using SNAP and the general workflow shown here, wherein an interferogram is created from two aligned repeat SAR images, then using the appropriate DEM, the topographic phase is calculated and removed. The 2016 Kumamoto earthquake in Japan has often been used as an interferometry example by the SAR community, as it shows, when processed like this, clear and easily intuited deformation results emanating from the epicenter. DNSAR processing using two images, one before and one after, result in distinct reading patterns of interferometric band or fringes representing the 2 pi radian value cycles of the wrapped phase. These phase fringe bands indicate surface deformation of half the sensor wavelength, or in our case, about 28 millimeters of relative displacement per full cycle as measured in line of sight from satellite to ground. Here we have the processed DNSAR results of the November 30th Anchorage quake in 2018. While of similar magnitude to the previous earthquake, the Anchorage quake was both significantly deeper and of a different slip type. These differences manifested themselves in the deformation phase results produced. While analysis of the processed results was beyond the scope of the project, it was reassuring that the relative deformation indicated by the wrapped phase result correlated positively with the official USGS shake map shown here. To take DNSAR further, one can unwrap the wrapped phase. Doing so is not a task that is easy or fast, and is in fact one of the most challenging and processor-intensive tasks of INSAR. However, doing so allows transforming the discontinuous phase gradient of the wrapped phase into a continuous phase gradient over the image area, thus allowing one to derive absolute instead of relative deformation values. To add phase wrapping to the DNSAR workflow required the use of SNAFU, as shown here. The wrapped phase result is exported from SNAP, unwrapped with SNAFU, then imported back into SNAP as a new phase band. Due to the processing time overhead and time required, it's almost always best to create a small subset covering just the AOI. Once this is done, however, using simple band math, one can transform the now absolute line-of-sight wavelength-based phase change values into, say, vertical displacement in meters, as shown here in this process example, wherein using the unwrapped absolute phase values of 8 temporally sequential interferograms from 9 SAR images were used to estimate the vertical displacement of a drill pad experiencing subsidence in the Kuparuk River oil field of Alaska. The next processed examples demonstrate another INSAR technique known as persistent scatter interferometric SAR, or PSNSAR. Whereas previously 2 SAR images were used to calculate phase shift, PSNSAR uses statistical time series analysis of many SAR images to derive phase value histories of discrete points. This technique is even more time and processor intensive than DNSAR, but typically generates improved overall results. To perform PSNSAR processing, first requires the use of SNAP. A single primary SAR image is chosen out of at least 15 to reduce the overall dispersion for the stack of interferograms that are created. This multi-interferogram stack is exported from SNAP. Then, STAMPS is used to find and calculate the unwrapped phase values of pixels that retain high coherency throughout all of the interferograms within the stack. The history of values at these so-called persistent scatter points can be used to plot deformation velocity or rate of change. Now, STAMPS doesn't just rely on SNAFU, but also, unfortunately, relies on MATLAB by MathWorks. It doesn't just need MATLAB for a specific function, like it uses SNAFU for phase unwrapping, but it runs using MATLAB scripts and entire pre-compiled MATLAB core functions. The open source MATLAB alternative simply didn't function as required, and the only reasonable solution was to activate a Linux version of MATLAB using a student license available to me via the university. This, however, enabled me to run a terminal version of MATLAB and therefore eventually gain full stamps functionality and produce PS-INSAR results for locations such as Kuparuk. Using 19 seasonal SAR images to produce a stack of 18 single primary interferograms, from which coherency values and wrap phase point values, plotted here by location and image acquisition date, were used to filter, unwrap, and derive the deformation rates at discrete persistent scatter points as shown here in this 2017 to 2018 PS-INSAR result of a section of the Kuparuk River oil field in Alaska. Likewise, the same workflow using 27 primary interferograms from 28 SAR images produced these PS-INSAR deformation rate values for Bethel, Alaska. As you can see, having the largest expanse of immutable surfaces, the pavement, the PS are primarily concentrated at the city's airport. Overall, the project's timeline remained as initially conceived, with only minor alterations made to increase the amount of time allotted and needed for DNSAR and PS-INSAR workflows. After installing an open source operating system, SAR image processing software, and interferometry specific software packages on available, marginally upgraded hardware, an interferometric capable open source SAR Workstation was assembled, and some of its capabilities and limitations were demonstrated with process results using freely available SAR data. The relevant workflows used to derive the results presented were documented, and a disk image of the fully functioning workstation was created to lessen the burden of setting up a similar system in the future. The main caution I would have for others interested in open source processing, SAR or otherwise, is to never underestimate how long free can take. There's often a reason why commercial software is expensive. Possible extensions of the project include evaluating the analysis capabilities and limitations of open source GIS, like QGIS, which was installed but only tangentially used for the project during workflow testing, or developing a solution to the MATLAB licensing requirement for stamps, perhaps converting it to use several of the MATLAB equivalent open source software like GNU Octave, or even, possibly better, a full Python adaptation of stamps. I'd like to acknowledge, in general, the entire staff of the UAA Department of Geomatics, both past and present, and the always helpful SAR community found at the ESA's STEP forums. If you have SAR questions, go there. And for the guidance and opportunities provided, without which this project would not have been possible, I'd like to thank Kaisha. Finally, I'd like to thank, with immense gratitude, my wife, Melanie. Thanks.